Hello learners, welcome to the course Psychological Assessment in Applied Settings, Module 5 Standardization and Norms. This is Lecture 5, Types of Norms, Part 2. In earlier lecture, the Types of Norms Part 1, I have considered and elaborated age-related norms, age-equivalent norms, grade-equivalent norms, and percentile rank norms. The another most important type of norms is standard score norms. It is actually basically what we do, we convert or transform the raw scores into standardized scores. These raw scores are transformed by two techniques. One is linear transformation and second one is normalized transformation. In linear transformation, we will discuss about z-scores, and in normalized transformation, I will discuss about Sten score, Stenine score, t-score and deviation IQ. These all are considered as standard score norms or roughly say standardized norms. So let's begin. First, standard score. It is actually a derived score. We know that the raw score which we get from a psychological test is actually meaningless without any interpretive data, and these derived scores help us to get any interpretation, to get meaning from that raw score, and the standard score is basically a derived score. It is specified of fixed mean and it has fixed standard deviation. For all these standardized scores, there are fixed mean and standard deviation. The standard scores have equal units of measurement and the size does not vary from distribution to distribution because all these scores are based on normal distributed scores, so it does not vary from distribution to distribution. The kind of problem which occur in age equivalent norms, grade equivalent norms are that in those norms there is no equal unit of measurement, but in standard score it has equal unit of measurement. The raw scores can be converted into standardized score or standard scores through these two methods. First is linear transformation and second is normalized transformation. So first we will talk about linear transformation, and z-score is a classic example of linear transformation. Here we convert the raw scores into z-scores. It is a linearly transformed standard scores and indicates that how many standard deviation of a score lies below or above the mean of that particular distribution. So it has a fixed standard deviation, that is 1, and a fixed mean is 0. It indicates the relative standing within a distribution in a normal distribution. The formula to convert raw score into z-score is given here. Here you may see that the z is equal to x minus m upon st. It means to convert a raw score into z-score, we should have the raw score x, the mean score of that distribution and the standard deviation of that distribution. If the z-score, the calculated z-scores, we get a positive z-scores after calculation, so it means that the score is above the mean. It means the performance is above average, whereas the negative z-scores indicate the score below the mean. It means the performance is below average. So, while using this formula, you can interpret the z-score finding as well. Suppose after calculating or transforming the raw score into z-score, you get a score of -3. You get a z-score of -3. So, it indicates extremely low performance or extremely low level on that particular domain. But if you get a z-score of +2, so it indicates very high performance on that area. Let's take an example. Suppose in an anxiety test, the mean score is 5, the data which we get from normative sample, the norm group indicates mean of 5, whereas the standard deviation is 2. It is indicated in that manual or in that norms group. Now we have to calculate the Z score for the person A whose raw score is 8, for the person B whose raw score is 4, for the person C whose raw score is 6. Suppose it is an anxiety test. So what will be the calculation? The formula is Z is equal to X minus M upon standard deviation. Okay. Now because we have here the raw score, like for the person A, raw score is 8. So we will put the raw score here in place of X. Then the mean score is 5, which is written here 5 for that particular norm group, and standard deviation is 2. So it is written here as 2. Now when we calculate it, 8 minus 5 is equal to 3, and here the standard deviation is 2. So it indicates the score of what? Plus 1.5. So here we get the Z score in positive. It means it is above average. Now calculate the score for B, person B, whose raw score is 4. So we will put the 4 here as X, 4 here as X. Then mean is equal to 5, which is already indicated here, and standard deviation is 2. So the calculation will indicate here the score would be minus 1, because 4 minus 5 is equal minus 1 divided by 2 is equal to minus 0.5. So here the Z score is in negative with negative value. It indicates below average. For person C, the raw score is 6, mean is 5, and standard deviation is 2. So here 6 minus 5 is equal to 1 divided by 2 is equal to plus 0.5. So here again we get the score, Z score in positive value. So here the score is above average, here again the score is above average, but here it is below average. As it is an anxiety test, so we can interpret this raw score as the person A has above average anxiety level, the person B is below average anxiety level, whereas person C has again above average or in the range of average anxiety level. So evaluation of Z score. Z scores are standardized score, most precise way of indicating position in any distribution. It is used to compare individuals' performance across different tests, because we can convert the raw score into Z score. So the score of anxiety, the score of stress, the score of depression, the score of academic anxiety, we can convert all those raw scores into Z scores, and then when these scores, raw scores, are converted into Z scores and in an equitable form, so we can compare all these scores. Then it is perfectly legitimate to calculate average of Z scores. So these are the merits of Z scores, but what are the limitations? Because when the scores comes in negative, so it is very difficult to handle via Z scores. Further, it is also very difficult to handle when scores are in decimal and in a large sample. Like if your Z score come like this, plus 0.253, so it would be very difficult to interpret. But if the score is not in decimal, like +1, -1, +2, -2, so it is easy to interpret. Further, because it is a standardized score, a linearly transformed score requires some basic statistical technique. So it is hard for students and client to interpret what does these scores means. And in common test reports which we give to the parents or teachers, these are not commonly used. But still, there are certain applications of these Z-score. These are very popular standard scores and norms because these are unit-free measures. You can convert the raw scores into Z-scores, and you can compare, after that you can compare all the scores of different tests or scales. So it gives a score comparability, and there is equal unit of interval. So it is very useful and very helpful scores. It allows easy standardization across different distributions, because if there is different distributions, there is different pattern in that sample, still it allow easy standardization. It is useful for comparing performance across different tests because we can compare or we can convert the raw scores of different tests in Z-score, and then we can compare all these Z-score. It also helps to identify extreme cases, like cases in which Z-score would be more than +2 or less than -2. It will indicate the scores is in extreme range. Again, we are just drawing here a bell-shaped normal distribution curve. What does it? It indicates this is the mean, and so from -1 to +1, area is 68.26%. From -2 to +2, the area is 95.44%, and from +3 to -3, the area is 99.73% in a normal distribution. But if any Z-scores which has more score than +3 and less than -3, like -4, -3.73, -5. So these are the cases of extreme cases. Through these Z-score, we can identify these extreme scores. Further, it is the Z-score is basis to convert all other standardized scores. Like on the basis of these Z-scores, we can convert or calculate T-score, STAIN, STAIN score, and deviation IQ as well. So all total, the linearly transformed standard score or Z-scores have all the properties of original distribution of raw scores. However, if there would be skewed distributions, either in positive direction or in negative direction, so in these two skewed distribution, you can't compare the scores. This is a limitation of this linearly transformed standard score. And a solution to this is to convert your raw scores into normalized standard scores. Like if you have the data, 2 data, 3 data, scores from different tests which is normally distributed, then it's fine to compare those scores. Then it is good to convert those scores into Z-scores and compare all these. But if there is positively skewed or negatively skewed data, the skewness pattern is different among those different tests, so you can't compare these two. In that case, you have to use normalized standard score, which is T, STAIN, STAIN, or deviation IQ. So now we will consider normalized transformation. So Marshall and Hales have defined normalized standard score as scores which have been what? Adjusted to produce a normal frequency distribution. It means here the scores are fitted or adjusted on a normal distribution curve, and then it is converted to a standard base with a pre-assigned mean and ST. Again, in normalized transformation, in all these scores, we have fixed mean and standard deviation. Like for Z-score, the mean was 0 and standard deviation of 1. Here in T-score, STAIN scores, STAIN scores, deviation scores, all have fixed mean and standard deviation. So here we adjust the scores, we fit the scores on a normal distribution curve, and then we convert the raw scores into these standard scores on the basis of fixed mean and standard deviation. There are some common normalized standard scores. So these are some common normalized standard scores, T-scores, Stenine scores or Stein scores, and deviation IQ, which we will consider. First, Stein score. The Stein scale, which is given or elaborated by Canfield in 1951. The name Stein itself suggests standard 10. So here the score are divided into all total 10 units. That's why it is called standard 10. Stein scores. It represents a range with a certain numbers of standard deviation from average, and the average result in this Stein scores lies in the border of 5 and 6. So mean of this, the fixed mean of Stein score is 5.5. So all the Steins 2, 3, 4, 5, 6, 7, 8 and 9, it covers a range of 0.5 sigma each. The Stein score range from 1 to 10. So here it is written like Stein scores range from 1 to 10. Only it doesn't go beyond the 10. If it goes beyond the 10, we will round off in 10. The mean is 5.5 fixed. Standard deviation approx to derived. It is the Stein score is derived from Z score using this formula. Like if we have the Z scores, we can convert those Z scores into Stein score by using this formula 5.5 plus 2Z. So suppose if we have a Z score of plus 1 and we put this plus 1 into this formula, it would be 5.5 plus 2 and here it is Z, that is plus 1. So the score would be 5 plus 5 plus 2 1 ja 2 and that is 7.5. This would be the Stein score for the Z is equal to plus 1. So Z plus 1 के लिए, for the Z plus 1, the score would be 7.5. Stein score would be 7.5. Interpretation of Stein score: if the Stein score you get, that is in range of 1 to 2, it indicates very low. On that domain, 3 to 4 low, 5 to 6 average, 7 to 8 high and 9 to 10 very high. You can see that we can see here the Stein score in corresponding to standard deviation. At mean, here it is 5.5, that is the fixed mean for the Stein. And as we goes toward positive direction in Z, the Stein score is increasing. We goes toward negative direction of Z, the Stein score is decreasing. So these Stein scores are in accordance with those standard deviation. Evaluation. So these Stein scores are very commonly used in personality and aptitude testing, allows finer distinction than as compared to Stenine, and it is easy for interpretation and reporting. But it is less precise as compared to the continuous score like T or Z. You may see here from my 1 to 2 sigma, the interval is quite equal, but here in 7.5 to 9.5 the distribution, and from this 9.5 to 10 the interval is not that much equal. Further, this Stein scores it has limited interpretive depth for clinical decision. It is not that much used in clinical decision, and in recent time these Stein scores are not that much used in psychological testing. It is used in personality inventories like in 16PF, EPQ and some occupational assessment it has been used. It simplifies the interpretation because not that much complicated for the students who don't know that much statistical techniques. It facilitates comparison across different subscales or different tests. It maintains equal interval properties like other standard scores. If we get an example, like if we have tested neo-FFI on a individual and candidates extraversion scores came on Stein 8. So it means high extraversion because the score is more than 5.5. But if the STEN score of that person on neuroticism is 3, it indicates low emotional instability because the score is less than 5.5. Next is stenine score. The difference between STEN score and stenine score is only that in STEN score we divide a score scale into 10 units, but in stenine we divide scores into 9 units. These stenine scores are developed by United States Air Force during World War II to recruit the army personnel. The stenine term reflects standard 9. It has a range from 1 to 9 because the scale, all the scores are distributed in the scale of 1 to 9. The mean is 5 and standard deviation is 1.96, or you may say approx 2. The average result lies in the middle of 5th stenine because here you may see the mean is 5. So, the average result, the mean of the stenine is 5. You can also derive the stenine from the Z scores using this formula 5 plus 2Z. If the scores would be in decimal, so you may round off the number to the nearest whole number between 1 to 9. Let's take an example. We have calculated STEN for Z plus 1. Now we will calculate stenine for when the Z score is plus 1. So here in this formula we have put 5 plus 2 and in bracket Z scores. Then 5 plus 2 multiplied by 1 is 2. 5 plus 2 would be 7. What if Z score would be minus 1? Then 5 plus 2 which came exactly from that formula. Here at the place of Z score we put the Z score of minus 1. So it will result 5 plus minus 2. Here the score would be 5 minus 2 is equal to 3. So for Z plus 1 the stenine would be 7, for Z minus 1 the stenine would be 3. Here you can see that we can convert the percentile score percentage to stenine. The first stenine contains a lower 4%, then second stenine contains 7%, the third stenine contains 12, fourth contains next 17% of scores, fifth contain next 20% of scores, sixth contain next 17% of scores, 7 contains next 12% of scores, 8th stenine contain next 7% of score, and 9th stenine contain next 4% of scores. So all total you may see that in the middle distribution, in the middle stenine there is high number of percentage, whereas there is less percentage in the extreme scores. If stenine score come from in the range of 1 to 3, we say that the performance or that level is below average. 4 to 6 average and 7 to 9 above average. This is a roughly estimate of interpretation for stenine scores. Here you may see, as we have already discussed, that on the basis of this Z scores you can interpret the stenine here also. You may see that in the middle of the distribution there is more percentage of scores, but in extreme scores, extreme stenine, there is less percentage of scores. Now evaluation of stenine. So what are the merits of this? Easy to report and understand, and it is used in educational testing and large scale assessment, but it is low precise because each stenine covers a wide percentile range. In middle of the distribution it covers a large range. Still from 1 to 2 it covers a large percentage of scores. Further, the small differences in raw scores can shift stenine category. The raw score which only converted from like 7% would change the stenine score from 1 to 3 in some context. But still, this test has been used in educational testing, aptitude assessment, and military classification test. As I have told you that to select or recruit military personnel in some kind of test, this STENINE score has been used. It simplifies the reporting for teacher, parents and administrations, but reduce precision and increase clarity for large scale evaluation. Let's take an example. If you test a student on any achievement test, a student get a score and you converted the raw score into STENINE, you get a raw score of STENINE score of 8. So a student would be higher achiever because the score is above average. But if the student raw score, you converted that in STENINE and you get a STENINE of 3, so it indicates that a student is below average achiever. Now T-score, first devised by McCall, and this test named T after Ian Thorndike. On the honor of Thorndike, this T-score has been given its name. It has a standard score which is based upon a mean of 50 and standard deviation of 10, as well as it follow a normal distribution in the scores. It based upon normalized Z-score scales, and the range of these scale is -3 to +3. In most of the case, it has a range of 20 to 80. How to compute T-scores? So, if you have Z-scores, you can convert the Z-scores into T-scores. For example, if a student's raw score is 80, mean is 70 and standard deviation for that particular group is 5. So, first you have to calculate the Z-scores. The formula for Z was x minus m upon SD. So, here the raw score is 80, mean is 70 and standard deviation is 5. The converted Z-score is +2. Now, to convert this Z-score into T, we have put these values in the formula. Here 50 plus 10 because it is written here, and Z-score, Z is +2 we have. Then we have calculated 50 plus 10 to the 20, 70. So, this is the T-score here. This is the interpretation of T-scores. 0, if you get the Z-score of 0, it will reflect a T-score of 50. As you increase the Z-scores, you will see a 10 increase in T-score, and as the Z-scores are decreasing, you may see a 10 score decreasing in T-score, and this is the average level. Scores below this will indicate low performance on that. Score above that score, T-score above that Z-score or T-score indicates high performance on these. Here you may see the Z-score and corresponding T-score on this normal distribution curve. Here you may see that with +1 Z-score, the T-score is 60. For +3 Z-score, the score is 80. For -2 Z-score, the T-score is 30. So, here in this range, we have 68.26% data. Here we have 95.44% data. Here we have approx 99.73% data. So, when we say that most of the cases falls under 20 to 80% of T-score, it means all total 99.73% cases falls under -3 to +3 or T-score of 20 to 80. These are very extreme cases in this. Evaluation. So, this T-score is widely used in clinical assessment, in psychological testing. It facilitates easy comparison across different tests, across different domains or scales, and it is developed to avoid negative decimal in Z-scores. When we have talked about Z-scores, the Z-scores, when the Z-scores come in the range of decimal points, so it would be difficult to compute or interpret. So, the T-score help us to get rid of those decimal Z-scores. But limitations, that the T-scores is arbitrary scale. It has lack of intuitive meaning for a simple person. It is still required a statistical technique and not easily related to real world behavior without any interpretation. So it is a standardized measure of intelligence. Earlier there was simple IQ scores, but David Wechsler has introduced this deviation IQ score, and it expresses how far a person's score deviates from the mean of their age group. How far a person's IQ score deviate from that particular age group in standard deviation unit. Here they have used the mean of 100 and standard deviation of 50. But for different IQ tests, they have different SD in the range of 12 to 18. But mean is fixed, that is 100. So the formula is here 100 plus 15Z. So if you have a Z of plus 1, so by putting this Z1 into the deviation IQ formula, we can calculate the deviation IQ. 100 plus 15, 1 is equal to 115. 100 plus 15, here the Z is minus 2. So it will 100 plus minus 15 to ja 30. It indicates 70. Below average scores on that IQ. It is overall comparison and overall summary, you may say, for all these standardized scores as in correspondent to these Z scores. We can see here the T scores, deviation IQ, ST9 percentile, all that is based on this normal distribution curve. So the evaluation of deviation IQ, it enables diagnostic and comparative use in intelligence testing and assumes that IQ follows a perfect normal distribution. So it is based on normal probability curve, but it may be influenced by cultural bias, cultural differences and test bias tendency, and overemphasis can lead to labeling or misuse in education. This deviation IQ provides a standardized comparison across different age groups. It is most popularly used in several Wechsler intelligence tests like WAIS, WISC and VPPSI and other intelligence tests also. It is very stable and statistical than the ratio IQ which was used earlier. For example, a 10-year-old student with 130 IQ performs better than 98% of same age peers. Here we use the deviation IQ because only using this 130 IQ, ratio IQ will not give us that interpretive data, interpretive findings as this one does. So in sum, you may see in Z score the mean is 0, standard deviation is 1. Similarly, I have given all the score types or norms scores, its means, standard deviation and the formula and the typical range of these scores. Now, today in this lecture, we have covered all the standard score, important standard scores, Z score, T score, ST9, ST10 and deviation IQ. And we have calculated that how on the basis of Z score, we can convert the T, ST9, ST10 deviation IQ. Normalized transformation, we can do that on the basis of Z score. So now a practice for you. Here I have given you a practice question. A student whose raw score is 65. He or she get a score of 65 on a arithmetic test. The mean for that particular group is 70 on that normative sample. The standard deviation is 5. Now you have to write the formula for each score. You have to calculate these scores on the basis of this raw score and you have to get the result for it. So start. First Z score, the formula is x minus m upon SD. Then we have put raw score of 65 here. The mean is 70 divided by 5 and the result would be minus 1. Minus 1. Yeah, it means for the raw score 65, the Z score is minus 1. The T, the formula is 50 plus 10Z. Here we have put 50 plus 10 and the z is minus 1. So here we have put minus 1 and the calculated result of t-score give us a value of 40. For deviation IQ, the formula is 100 plus 15z. Now the z score we will put here, that is minus 1 and the calculated score would be 85. Stenine, the formula is 5 plus 2z. We have put the values in the formula and the result is 3. And for the last Sten, the formula is 5.5 plus 2z. We have calculated the Sten score 5.5 plus 2 as it is from the formula and then minus 1 here from this z score and the value is 3.5. Now we will convert it, we will take a whole Sten number and that is close to 4. So here the Sten score is 4. So all total, all these indicators indicate below average performance on this particular test of this person. So all total we have covered all these things. Happy learning. Thank you.